Yeah, yes, I did mark you here. And so you've got a situation where the Earth is part of the solar system, and as such, it is in the proximity of our sun. So we get the rays of light from the sun coming into the Earth, and they're virtually parallel. Maybe a little diagram here is called for, right? So I'm going to draw sort of the sun as a big circle over here. Okay. And which ways do the rays of sunlight emanate from the sun? Well, they emanate out directly outwards, right? So they're not exactly parallel, right? They all emanate from the center of the sun, more or less. And but you know, if we were to put a scale picture of the Earth, it would be like a little dot out here, like that, right? And so the rays of the sun coming into the Earth are virtually parallel, right? At the point where they hit the Earth, this little black dot here is the Earth. They are essentially parallel. So there was a fellow by the name of Eratosthenes. There's a silent H there. I think he's like 250, what do they say? Before the Common Era, BCE, something like that, right? So long before Columbus convinced Queen Isabella of Portugal that the Earth was round, and in fact, its radius was small enough that you could sail from Portugal to the East Indies by going west, right? Because you'd come right back around this little round ball of the Earth and end up in the East Indies. And I remember receiving this story as well. People at the time thought the Earth was flat. No, that's not true. People did not think, I mean, some people maybe, some people still think the Earth is flat. Which, I mean, your local evidence is, yeah, kind of, you know, you don't see a lot of curvature directly around you, although, you know, if you're looking at a ship going out to sea, you kind of see it falls below the horizon, so maybe it's not perfectly flat. In any case, if we draw the Earth, let's make another circle here for the Earth, okay? And where's the center? Right here. Huh? And, okay, sorry, this is, and so, you know, let's say that the rays of the sun are coming in like so, right? Parallel. These are parallel lines coming in. Not exactly parallel, but close enough for our purposes, right? And if you have a point, say here at Alexandria, which is the city in Egypt, actually, at the mouth of the Nile. It was sort of an international city at the time. Eratosthenes was Greek, but there were a lot of Greeks living in Alexandria. If you walked 500 miles south, you got to a place called, I don't know, Cyrene or Cyrene. I'm not quite sure how to pronounce that. So this is 500 miles, or I think actually they measured in stadia, which was, you know, the distance across the stadium, which was, you had professional walkers, right, who would pace off stadia. And you could do this for 500 miles, apparently, and get a pretty accurate measure. I think, you know, Egypt pretty flat, kind of desert-like. So, yeah. And so you've got, at say 12 o'clock on a particular day, the sun shines directly straight down into a well, say in Cyrene. And so you can see that it's directly overhead, right? 500 miles away, that same sunshine coming from the same sun at the same time doesn't shine directly towards the bottom of the well, right? It makes a little a shadow whose angle you can measure, right? And they measured that angle to be about 7 degrees. And what do we have here? Can I look back over here? And 12 minutes. And so that is this angle, and we have the radii of the Earth. So let me go back to my drawing here. So this angle here is 7 degrees, 12 minutes. This arc length is 500 miles. That's on the surface of the Earth. And we have the 2 radii. So it turns out that the ratio of arc length to central angle subtended by that arc length is the same for any arc length and any angle, right? So arc length per central angle, and that's going to be 500 miles for between Cyrene and Alexandria, Cyrene, I don't know how you pronounce that. And the central angle is, well, should we convert this to decimals? So what's 12 minutes? Well, you're going to multiply that by 1 degree per 60 minutes. 1 degree equals 60 minutes, right? We talked about degree measure, right? Yeah. So am I monitoring the chat? No. Okay, there's nothing there. And so this is going to reduce, 12 times 5 is 60, right? So this reduces to 1/5 of a degree, or 0.2 degrees. So we can say that this 7 degrees, 12 minutes is 7.2 degrees, right? And that's, so what's the other one we know? Well, we know that the circumference of the Earth is 2 pi r, and that's just a formula, right, for the circumference, and that's 360 degrees. So if you go the whole way around, the arc length is the whole circumference, which is 2 pi r. So here's an equation with only one unknown, right, r. And so Eratosthenes was able to solve this equation. What can we write? We can write r, divide both sides by pi r and multiply both sides by 360. Sorry, divide both sides by 2 pi. So half of 500 is 250. And we're dividing by pi. So I already divided by 2, right? And then 360. Well, I'm going to write 3,600 divided by 72 and just get rid of, multiply by 10 over 10 to get rid of the decimal. So that should be the radius of the Earth in miles, right? Because we're measuring in miles here. Does this thing reduce here? Well, let's factor. I think there's a factor of 9 here and a factor of 8. So I think this is going to be 250 over pi. Let's just leave that. But let's say that this is 9 times 400, which is 8 times 50. And this is 9 times 8. Right? So that's kind of convenient, right? So the 9 times 8 cancels out. And we get, I think it's 1,250 divided by pi. which is approximately, oh, I think I'm off by a factor of 10. Yeah. I mean, these are correct, right? I just didn't have another, I needed another factor of 10 to make this correct, right? And let's say that this is approximately 4,000 then, which is pretty darn close, 4,000 miles, right? That's a really pretty good estimate for the radius of the Earth. I think it's, 3,960, right? So it's like 40 miles off. So it's about 1% error, maybe. So Eratosthenes knew this. Cognoscenti, the learned people of the Earth, knew this in the time of Christopher Columbus. So that, Christopher Columbus either knew this and lied to Queen Isabella about the length of the trip, or he actually thought that was true. He had done the computations wrong. He thought it was like 1/4 of that, right? He wouldn't have tried to travel, because I mean, what does this mean? The circumference of the Earth is, right? Circumference is then approximately, I think twice, right? Multiplied by 2/2, you get the circumference is 25,000 miles, right? So I don't think Christopher Columbus would have attempted a trip that long. He didn't have provisions. He barely had provisions for making it to what we now call the West Indies. So he got lucky. There was a landmass between him and where he thought he was going. But he thought he had hit the East Indies, right? All right. Supposedly. I don't think he cared much. He just wanted gold. So either he was a liar or an idiot. That's why the mail is not being delivered today. And so on. Okay. So let's, all right. So let's get down to matters at hand. So that's actually a nice bit of, and let me put the address for this website that kind of describes. There may be better websites. This was the best one I could find in a short period of time. I'll put that in the chat. Everyone, yeah. www.geo.hunter.cuny. That's the City University of New York, where they're suffering under the dictatorship of Capo Cuomo. I'm from New York, so I take it personally. All right, so, okay, where are we here? Courses, trigonometry. Okay, so we need to add a module for our new week. So the module is going to be module 7. Week 7 module, I think is the, and so this is going to be all about compositions and inverse functions. And that should wind it up. Add module. Okay, and I think I have to go to the bottom and move it to the top because the default is to have it at the bottom. Okay, and should we move this up to week 7? Yeah, so these things here, I added them as homeworks so that, if you wanted to have them appear on the homeworks thing where they should, or you wanted to have another shot at it, went ahead and added those there. But these guys, let's move them up as well. Okay, so now we got all these guys here, and this is sort of inconsistent, huh? If I'm going to capitalize functions in one, I should capitalize it in the other. There. So, oh, sorry, we're not looking at that, are we? Okay, so here I've got the week 1 module. Are we recording? We are, huh? Okay, good. Right, and then we have the text, which is here. And do I have that? Yeah, okay. So we had this was, I think this is the transformations section. Yeah, and there's a section on even and odd functions. Determine whether the function is even, odd, or neither. So yeah, let's talk about that. That's an important notion having to do with if a reflection doesn't change the actual appearance of a function, it's the same appearance before and after the reflection, then it either has even symmetry or odd, well, then it may be even or odd symmetry. And that's a discussion in the next little set of problems. But let's go ahead and define what that means. Okay, so definition. F of x is an even function. That's what we're defining here. If and only if, I guess, that's the double F, f of negative x is the same as f of x. So why is it called even? Well, this is true for polynomials where all the terms have even degree, right? So an example would be like f of x equals x to the fourth minus 3x squared minus pi. Pi is just a constant, right? A constant, you could think of that as times x to the 0, right? And 0 is considered to be an even number, right? Evenly divisible by 2. 0 divided by 2 is 0, right? So then f of negative x, well, what does the function do to its input? It takes the input, which is important. You put it in parentheses here, right? Because you're going to act on negative x now, right? So we're going to raise negative x to the fourth power. Then we're going to subtract 3 times the square of negative x. And then this pi is still just pi, right? But, an even number of negative factors, it didn't matter that they're negative. The negatives cancel out, right? So this is the same thing with negative x times negative x. That's just x squared, right? And so that is f of x, right? So that's an example of an even function. Let's see, okay. And odd functions. F is odd, an odd function, if f of negative x is the negation of f of x. So that's an example of what's called origin symmetry. Why is this guy? It's kind of tilted. Can I tilt it back the other way? Okay. So if you change the sign of, so for an even function, if you change the sign of the input, it has no effect on the output. For an odd function, if you change the sign of the input, you also change the sign of the output. So now the picture for even symmetry is, if you have A coming in, you get the same output, f of A, as if you have negative A, right? And so you have a reflection across the y-axis, right? F is odd if f of negative x equals negative f of x. So what that says is, in terms of the graph, is that, if A is coming in here and you got f of A coming out, then if negative A goes in, then you get negative f of A coming out. And that's origin symmetry. So you can kind of think of there being a line through the origin like this, where this segment here is congruent to that segment there. right? That's origin symmetry. So this has y-axis symmetry. And this has origin symmetry. And let's have an example. So now the reason it's called odd, guess what? If you have a polynomial with all odd exponents, then it's an odd, it will have that odd symmetry, right? So for example, f of x equals x to the fifth minus 7, or let's say 8x cubed plus square root of 2. Again, that's just a constant, right? Square root of 2x, right? Yeah, otherwise that would be an even term, right? So x, is to the power of 1. Or you can think of it that way, right? It's an authentic math paper. It's got the coffee stains already on it. Pay extra for that. So here, f of negative x is going to, well, you do to negative x what the function says to do to x, right? Square root of 2 times negative x, right? Well, if you have an odd number of negative factors, then the negative sticks, right? So that's the same as negative x to the fifth plus x, 8x cubed, right? Because you're going to have a double negative here. And then minus square root of 2x, which is the negation of x to the fifth minus 8x cubed plus square root of 2x, which is the negation of f of x, right? So that proves that this function is odd. It satisfies that condition. And yeah, that's powerful. If you can get this kind of symmetry happening, then you can sort of cut the amount of work you have to do for analysis in half, more or less, because you have, the symmetry can really be a powerful tool. Anything else to say about these guys? So let's go back to the text. Were there any exercises you wanted to look at in here? Did we finish looking at these transformations? Maybe we should take a look at these, huh? Let's go back over there. So we did a few of these, but maybe take a look at a few more. Yeah, we kind of did these, didn't we? Yeah, so these are all just shifting, right? One way or another. Oh, what's this one? Move the sliders H and K. Oh, look at that. So H equals 2 means that we're shifting 2 to the right. K equals 1 means we're shifting 1 up. And so on, right? Don't forget to shift the graph. Oh, what gets shifted 1 unit, up 1 unit. Okay, so 1 unit up and 3 units to the right. Okay. Then type the new function in the answer box. Well, they just copy it from here, right? Let's see if we expand it though. Can we expand this? So we get x squared minus 6x plus 10, right? 9 plus 1. Let's see if they accept that. Using the function notation, enter the function that results from the transfer. Okay, I think they want us to then actually type f of x. Whoops. Can you see this? Yeah. F of x equals, I'm going to write x squared minus 6x plus 10. And there's the pretty type. If I hit submit, yeah, it recognizes that, but would it also recognize what we have there, x minus 3 squared? I mean, do you have to expand it? I don't think so. I submit that. Yeah, it also accepts that as correct, right? It's got artificial intelligence. That's creepy. How does it know? Yeah, no, it's just programming. It's not, there is no such thing as artificial intelligence. I know that makes me a controversial figure to say that, but no, it's all just programming. I think there's real stupidity, but you know, that's also a human thing. How are we doing? 13? Oh, that's 13 is another one of these, huh? 10. Yeah, so then just draw the dots and put them in the right place, right? Okay. Questions, but you want to see any one particular one of these? Or let's see, there's a question here. So we're not really solving the problem if the answer is negative f of x. I'm not sure which question, what's the question? Yeah. I mean, yeah, so we were talking about odd symmetry. And yeah, I mean, that's the problem is to demonstrate, as we did here, we were demonstrating that this function, f of x with these odd powers 5, 3, and 1, is in fact an odd function. By plugging in negative x and seeing when we work that, we get, in fact, the negation of f of x. Okay, so I'm going to go back over here, and I guess I want to go, oh, I didn't want to go there. Modules. Okay. So composition of functions, what do we got here? No. So yeah, let's just work some of these problems. I think, you know, these may be parametric, so I'm not really spoiling it for you. If you'll probably have different coefficients, is that right? Anyway, it's not much of a spoiler if I work it anyway, right? Okay, should we zoom in on this a little bit? It tends to be kind of small, right? And I think we can get rid of that, right? Okay, so here we have a linear function, 5x plus 2 is the formula, and a quadratic function, 5x squared plus 4x. And they say after simplifying, simplifying is not a simple term, right? It can mean different things in different contexts. It's sometimes a judgment call, like on the one we were just kind of looking at, where I expanded the square and collected like terms. Is it simpler after doing that, or is it simpler in vertex form? So in some sense, the vertex form is simpler, right? Depends on the context. Well, let's see what happens here, right? So the picture of what's going on, and let's go to the drawing board here, is, okay, so this is two functions. F of x is 5x plus 2, and g of x is 5x squared plus 4x. All right. So f of g, now that's like a little o, right? So when you see that little circle there, you can think of that as the word of, f of g of x, which another notation for this is f of g of x, like that. So the output of g is the input to f. And another picture we could draw is x comes into the g box. The g box processes it, whatever formula or method, and produces as an output g of x. The output of g goes into the function f, and out comes f of g of x. Okay, so let's process this with these formulas, right? So in this case, f of g of x, and I tend to kind of prefer this notation because I'm going to substitute the formula. G of x is 5x squared plus 4x, right? So what does f do to its input? It multiplies it by 5 and then adds 2. So if this is the input, we're going to multiply this by 5 and add 2. Right? Okay, I would think we would all agree that's not in simplest form, right? So what would you do? Well, you'd expand this product here, distribute the 5, right? So you'd get 5 times 5 is 25x squared. 5 times 4x is 20x, and plus 2. Is that simplified? Well, yeah, it's in one of the simplified forms. It's in descending powers form, right? So I bet if we were to enter that, it would accept it. However, can you also write it in vertex form? Nah, how would you do that? Well, you'd factor out the 25, right? My collar is not straight. So that's the first step, right? So to complete the square is what this is calling, right? To call when you want to get vertex form. So the first step is to factor out the 25 from the terms involving x, right? So 25 times what is 20? Well, you could write 20 25ths, right? But that reduces to 4/5, doesn't it? Yeah. So I'm going to say plus 4/5 x. Then I'm going to leave a space there. And what goes in the spot where the space is? Yeah, I'm just looking at the comment. There's a private comment here, so not everybody sees it. But yeah, this was going back to the odd function. And yeah, that was just a theoretic thing. There was no actual, oh, there was a function. Yeah, there was an example of a function, right? So we were just demonstrating that that particular function is odd. That was all we were doing. Yeah, there's no equation to solve, right? Okay, so what's the rule for completing the square? Well, if you have a leading coefficient of 1, which we do here, right? Then you take the coefficient of x, which in this case is 4/5. You take half of that, half of 4/5 is 2/5, and square it. So I'm not actually going to compute the square here. I'm just going to indicate that it is the square of half the coefficient of x. That completes the square, but it also, destroys the equality, right? These are no longer identically equal for all x. So to balance it, I have to subtract what? Well, not just this, but 25 times that, right? Because everything in the parentheses here is being multiplied by 25. So I'm going to subtract 25 times the square of 2/5. I'm just going to write it like that, okay? And we can worry about simplifying it later. Yeah. So now these are identically equal. No matter what x I plug in here, I'll get the same value if I plug in that x here. And it does look a lot worse at this stage. I mean, more complex looking, but in fact, the whole idea is to make it look simpler, right? So this is going to be the square of x plus 2/5, right? When you square this binomial, you get that trinomial. That's the whole idea. Right? Twice the product of the 2 in the middle, twice 2/5 is 4/5 times x in the middle. Now, what is all this? Well, actually, I think this is conveniently easy to simplify because we get the square of 2/5 is 4/25 times 25 is 4. So 2 minus 4 is -2. So that shows that the vertex is at negative 2/5, right? Because it's x minus h, so h would have to be a negative. K is negative 2. Well, they don't ask for the vertex, right? But I'll bet you if I put it in this form, so let's try entering that and see if it accepts it. I'm sure it would accept the other form. But if I put in 25x plus 2/5, like that, yeah, squared. And notice it's typing the pretty type below, so that's good. And minus 2. Should we put in a reality check? So we said that that this descending powers form is equivalent to this vertex form, right? And if x is 0 here, then f of, well, this function is equal to 2 when x equals 0, right? If I were to plug in 0 here, I'd get the 0 plus 2/5 is 2/5, squared is 4/25 times 25 is 4 minus 2 is 2. So they agree, which is a good thing, right? Sometimes just one little reality check is a good thing. Okay, so I'm going to, if you need help, you can watch the little video. I'm sure they're not going to complete the square in the video, but yeah, see, they also accept this. I don't think you're required to put that in, right? We can just put in 25x squared, what is it, plus 20x, plus 2. And we could submit that. And yeah, it likes that also, 2 as well. Is there another standard form we could put it in? Yeah, I hesitate. The other standard form is factored form, right? But this is sort of algebra 2 stuff, which people tend to forget, and you're going to want. So this is the ax squared plus bx plus c form, right? And this is the a times x minus h plus k form, right? What's the other form? Well, that's a times x minus r1 times x minus r2, where r1 and r2 are the x intercept values. The x values where y is 0, right? So if x is equal to r1, this factor is 0, that makes the whole product 0. Likewise, if x is equal to r2, then this factor is 0, making the whole thing 0. So how do you find the zeros of a quadratic? Well, there's the quadratic formula. But if you have vertex form, that's sort of easier. So you'd set 25 25x plus 2/5 squared minus 2 equals 0. That's going to say that x plus 2/5 squared, add 2 and divide by 25. So you isolate the power, the square, isolate the square. And why you isolate the square? Well, you want to extract square roots, right? So that says that x plus 2/5 is equal to plus or minus the square root of 2, and on the bottom we have the square root of 25, which is 5. And then you can add negative 2/5 to both sides. And this is kind of what you'd get if you were to plug into the quadratic formula and simplify, although it might be harder actually to plug into the formula. You get these two values. So this is one of the, if you add, that'll be your, say, R1. If you subtract, that's R2, or the other way around. But yeah, so that's this is going to be, A is what, 25? And so x minus what, negative 2 minus square root of 2 over 5. Yeah, that's kind of a gnarly thing. And then x minus -2 plus the square root of 2 over 5. And that would be your factored form. You can see why I hesitated to write that, because it looks pretty gnarly. It's because the roots are irrational, right? They're real, but they're irrational. Okay. And I'll bet you they would take that too, but I'm not going to write that in. Let's go on to problem number next. Or maybe we should do some theory first, right? And where's the theory? The theory is in the book. All right. So combining sums, difference, products, quotients, compositions, right? And applications of compositions. So given any two functions, you can add them together and get another function. So, you can call that function f plus g of x, or you can simply say, that's computed by adding f of x, the output of f, to the output of g. And that's a new function, right? You can also subtract. Domains are then the intersections of the individual domains. So if the domain of f is a and the domain of g is b, then to be in the domain of the sum, you have to be in the domain of both f and g, right? Kind of makes sense, right? So here they're adding, subtracting. You can also multiply the function outputs or divide the function outputs. Division has the extra caveat that the output of the divisor can't be 0, right? Oh, this is kind of fun here. What's this? The iterates of a function? Yeah. At a point are the numbers f of x, f of f of x, f of f of f of x, f of f of f of f of x, and so on. We examine iterates of the logistic function, which models the population of a species with limited potential for growth, such as lizards on an island or fish in a pond. Iterates of the model can help us predict whether the population will eventually stabilize or whether it will fluctuate chaotically. You can find the project at stewartmath.com. I don't know, should we go there? To get there, I guess we have to go here and then type in stewartmath.com. Yeah, we're using this book, Discovery Projects, Iterates and Chaos. That's project 11, huh? Oh. Okay, so here's your initial input, x naught, right? You plug that into the function, you get to the output, f of x naught. You take that as the next input, right? So the way to sort of visualize that is that you map the output to the input, and that happens on the line y equals x, right? If y is the output and x is the input, then the output equals the input if you're on the line y equals x. So you sort of map it horizontally over here. So that's your new x1. So the output of f of x naught is x1, and that's the input for the next function value. So f of x1 is f of x naught. And you just keep doing that process, right? Mapping the output to the input. And this is what happens when you, so you're going to sort of spiral in towards this point of intersection where you have a stable equilibrium. All right. I'm tempted to get out the calculator to do this because it's kind of fun. Do you have a TI calculator? Let me see if I can find TI calc. TI, I'm looking on my computer for this thing. Oh. Virtual Texas Instrument. No, it's not finding it. I know I've got it on here somewhere. Let me see if I can search my directories for it. It may not be worth the time, but it may be worth the time. I don't know. There's probably a website where you can, or we could do it on GeoGebra, right? VTI. Oh, I want to find this on my computer somewhere, right? So I'm going to look. I don't know. Search that drive for VTI, which I can show you where to find this probably on the internets. It's not finding it. It's a long search though, so the search is about halfway done. I'm watching a progress bar. Should I bring it over here? You can see what I'm doing there. Okay. I'm searching for VTI on my computer. I know it's here somewhere. I just haven't played with it in a while, so I don't know exactly. There. Okay, so we're getting a few hits here. Oh, these are in, yeah, that's not what I'm looking for, I don't think. Probably easier just to find it on the internets. So I'm going to say virtual TI. TICalc.org. That was the, yeah, been a while. Visual TI 89. Virtual, I mean. Okay, so what happened to my search here? I'm still searching, but it's not finding. Okay, let's just use, I'll maybe do this on my own time, find that for you. And I could post it up somewhere. Or you could download from one of these sites and install, but then you also have to find the shell or whatever it's called. And that's proprietary, so they can be harder to find. Okay, so what are we looking for here? Well, let's just go to GeoGebra. Okay, so let's throw in a few parameters. So I guess, let's see. So they've got a, I'm sorry, I'm looking at the wrong thing here. They've got a function that goes through the origin, right? And it's got some other intercept out here. Yeah, it's of the form kx times 1 minus x, right? So it's got intercepts at 0 and 1, right? If x is 0, then the output is 0. If x is 1, then this factor is 0 and the output is 0. But there's this parameter k, right? So let's introduce that parameter here in GeoGebra. Hello, GeoGebra. So I'm going to call it k. Whoop. I'm going to call it k. And I'm going to say, yeah, it ranges from, oh, I don't know, 1 to 4 maybe. Okay, then I'm going to enter in the function k times x times 1 minus x. Yeah, that's correct. Although we should probably zoom in on the area of interest, right? Which is here, right? And then as k gets larger, notice that the intercepts don't change what changes is, how high up the vertex is, right? So we spread, that's called a vertical stretch, right? We're stretching away from the x-axis. Can we move this down? Oh, sorry. Yeah. Okay, so let's draw in the line y equals x as well, right? Okay. And let's have an initial value somewhere between 0 and a half. So I'm going to make another I'm going to call it x naught. And I'm going to say that's between 0 and a half. Okay. Then I'm going to draw the initial input is then the point x naught comma 0, right? And so notice if I move this slider, that goes back and forth, right? So then I want to plot where does that go on the function? Yeah, and that's going to be the point x naught comma f of x naught. Does that work? Yeah. And I can draw a line segment connecting those two things, right? Okay. Now I want to take that output and map it back to the input. So I want to take the point on the curve, sorry, on the line y equals x, right, which is going to be f of x naught, comma, f of x naught, right? So there it is mapped onto the line. Let's draw the line segment connecting those. And notice as I change this, that, yeah, all of those things stay the same. What happens when I end up, oh, I can't end up over there. Okay. How about if I change, yeah. Okay. Yeah, makes sense. Any questions about that? So the new input is this point. Let's draw it on the x-axis, right? So that's going to be f of x naught comma 0, and I then want to map that to its output on the function curve, right? So that's going to be the input is f of x naught. The output is f of x. Oops. X naught. Right? Okay. And they actually connect these with, they say, okay, this is a dotted line here. Can we make it dotted? You don't see my dialog box, but I'm changing the line style in the dialog box to make it dotted there. And then let's make this just solid. All right, and then we want to map that back to the line y equals x. Same thing we did before, right? But while we're at it, we might sort of move things around, just experiment with this a little bit. Yeah. Okay. Okay, so things just keep doing the same thing, right? So the output is going to be f of x naught, and that's going to be mapped back to the input. So we want it to point on the line y equals x. It's going to be f of x naught, comma, f of x naught. There it is, right? I'll connect those with the line segment. So we're taking the output of the output, well, the output of the f of x, yeah.
You get the idea, I hope. So then I want to find where is that on the line on the x-axis, right? So map this back down to the x-axis. All right. That's going to be at the point f of x naught, comma 0, right? There it is. Now we'll connect these with a dotted line. We're having too much fun here. This shouldn't be allowed. Oh, we're out of time. Oh my goodness. Yeah, that's what happens when you don't pay attention to the time. Okay, and then I want to map. Okay, so well, we have 1 minute. So I'm gonna go to the next point here, which is believe it or not, f of oh, sorry, this is just the x value, but for the y value, we're going to say f of x naught. Right, there it is. Okay. Now we can connect it with a little there. Okay. So do we see anything interesting happening here? Not really, huh? Oh. Kind of something interesting. Yeah, so we can kind of see what was going on over here in this picture, right? Okay. And there's a lot more to say about this. You actually have a little program. You can program the TI-83 to do this, or you can do what we're doing with GeoGebra and get similar results. Kind of the GeoGebra one is a little better in some ways because you can kind of see the whole thing going on. Yeah, so then that takes us sort of back to our text or the problems. Yeah, did we get started on these? What's the next one like? Is it the same sort of thing? Yeah. So what's g of 0? That would be 6. And f of g of 0 would be then 48 plus 9 is 57, right? And notice that when you reverse the composition, you don't get the same thing. So it's not a commutative operation, right? So f of g of 0 is not the same as g of f of 0. F of 0 is going to be 9, and g of f of 0 is then going to be 6 minus 81, or negative 75, I think. Does that work? Yeah. All right. Well, keep reading in the section on compositions. Tomorrow, maybe we'll finish that up and get started on inverse functions. Any questions about any? Yeah, go ahead.
When are the tests going to be graded?
Yeah, I discussed that a little bit earlier. It's taking me a little bit longer than usual because I have to figure out a whole new way of like processing these things. And there are a couple of other tests in the queue before yours. So
okay,
I'm done with one of those. I'm started on the next, and after I'm done with those, I'll start yours. But that was geometry, so it doesn't really relate so much to what we're doing now. So
yeah, I know.
maybe,
I just wanted to know if
of course, I
what my score was.
That. Yeah.
Okay.
Yeah. And thanks for the question. Anything else? What sections should we read to prepare for tomorrow's class? I would just read this section on compositions. And if you have some extra time, get started on inverse functions. But yeah, you might want to experiment with this discovery project. It's pretty cool stuff. Chaos. Yeah. Sensitivity to initial conditions. Kind of an interesting, yeah, I mean, as in some sense, as simple as this is, it's very deep as well. So, all right, anything else? Okay, I don't want to impinge on your time. Plus, I'm expected in my office, so I will wish you a pleasant afternoon and see you later.
Professor?
Yeah.
Could we, would I be able to discuss something with you after class?
Sure.
privately?
Yeah. Let's, can you schedule a meeting in office hours?
I was trying to do that. I'm not sure how to do that.
Okay, let me spend a moment. So let's see if we go. Oh, sorry, I think I do want to be here, right? Okay, so I want to be here, and then I think it was it week 2 or week. How to use office hours. Okay, so there's a little. So you go to the class tile via dashboard on Canvas. Once in class, click on Confirm Zoom, then go to Appointment Booking. Do you see a link like that? And you can then click on an appointment with and choose the name of your instructor. Then you view the available slots via day or week. I think I can also do this, which, see if I go here and I say account settings, you can see my meeting ID is 530648. Or maybe go to this link. Let me copy that and put it in the chat here.
Yeah, I could see that I could book one for 12:25, so like 10 minutes.
Okay. All right. I'll see you then.
Okay, thank you.
Yeah. Oh, and there's that, I think, oh, I'm sorry, that was to, yeah, let me try that again. There. I don't know that that's going to work. Let's see what happens when I paste that in up here. Nothing. It's just completely ignoring me. Not sure why. But yeah, I'll go there and see you then.
Okay, Professor.
Bye,
Thank you.
everybody.